morning. So good morning and good afternoon for those of you joining from either side of the Atlantic. Yeah. So today we have this course, which is calculation of bottom hole pressures in Whitson Plus, and I will be. My name is Milan Stanko, and I will be hopefully teaching most of it. And then we have also online Mohammed Dahouk. He's also going to help me if I get in trouble, especially with the exercises. Let's see if I flip. Can you see if it is changing? I hope. Yep. So first, some general information. This is what corresponds to half-a-day course. We will try to have some maybe 1 or 2 breaks. I don't want to make it too intensive. We should have some, some pause for a bathroom break or drinking. I also want to, if there are any questions, I think the best way is that you write them in the chat, and then Mo, he will pass them to me, or he will stop me if there is something. And then if we need to clarify, I think they are going to open the mic to let you speak. And questions are welcome. I think that many people, when you have a question, some other people might have the same question that you have. And if there is something that is unclear and it could be very important to go forward, I think it's important that you so simply say it out loud such that we can, clear that out early. Of course, there are some things that might come later, and that I will let you know when that's the case. Okay. Yeah, so that's this. If you can put them on the chat, or you can unmute to speak. And we sent some material before the class, today. So you should have gotten an email from Jessica with the slides and and some information about how to log into the platform. I also added 2 more slides that are not there. I did it this morning, and we will share those with you also. So an updated version if you want. And just be aware that some things are presentation. So I will be especially the theory. The first part you will see it's presentation mode, and then the other part will be when we are doing the exercises. They are just for reference. So the images you see on the slides might be a bit different from what we're showing on the software. Okay, so regarding software, we're going to be using Whitson Plus, this cloud-based tool from Whitson that you can access through your web browser. Many of you have company domains, so don't use that, please. Just use this courses.whitson.com. We don't want to mess up any of your actual fields and your actual data, so you're going to use this course domain from Whitson. So be sure to log into that one. The username will be your email that you used. You registered to this course using your email. So use that as your username, and then the password will be BHP all capital, Whitson all the lowercase, and then 2025 and exclamation mark at the end. So exactly like this. Okay, so hopefully that's working for you. If not, please reach out to Mo, and he will help you with that. Okay. Recommended browsers, you have Google Chrome, Firefox, or Edge, but it's not supported any longer, this Internet Explorer. I'm not sure if anyone is using it still. Okay, so the agenda, what to expect. We are going to cover the bottom hole pressure calculation fundamentals. So first, I don't think we should dwell too much into the first point, but just to remind you why we calculate bottom hole pressures. What do we need as an input to those calculations? How do we perform the calculations? Then to make the calculations, we have to assume, or we have to get some flow path that we need to have on the well, either if it's tubing, casing, or something else. And then we also have to know if there is any artificial lift installed in the well. And then we talked, we're working with real data, so we always have some very spiky behavior. So if it's a need for smoothing and tuning, and I think this estimate initial reservoir pressure with IPR, that's I think a feature we have available in BHP. And then the second part we'll have exercises. We're going to not only to tell you about the theory, what things you can do in the software, but actually like a hands-on um, practice with the software. Okay, bottom hole pressures. Typically, it's very central in all the workflow, especially for unconventionals, but also for conventional reservoirs. We have the fluids and PVT. We have to get those in place, develop a fluid model that works, and usually central to that, we also have the pressure drop calculations, and usually they are to calculate. We have surface pressures, either casing head pressure or tubing head pressure, and we want to calculate what happens in the sand phase at the sand phase. And then that's part of like all the workflow. Like in this case for unconventionals or conventionals, we might have this flowing material balance, we might have RTA, or we have some kind of reservoir simulation. Okay, so that's what you will get with Whitson Plus. It's essentially this chart. You're going to get bottom hole pressure versus time for all the data you have provided. And the philosophy of Whitson is that we not only provide just one correlation or one model, but we provide simultaneously all the models that are available. So in this case, these are the four that are available: Bex and Brill, Hagendor and Brown, Boldesemayat and Gallard and Gray. That's a long name, sorry for that. So we want to print all of those simultaneously on the screen, so you have an idea, how your bottom hole pressures might look like. If you have data, then you can compare and see, well, which one fits or is closest. But if you don't have data, you're a bit aware of the uncertainty. One thing that is important to mention is that there is usually high uncertainty in these calculations. We cannot expect kind of a 1% accuracy or 0.1% accuracy. Usually, if you have a very good model and a lot of work has been done for the people by people trying to develop a very good model, usually you're happy with some plus minus 20%. Okay, so just be aware of that. So it gives you some spread that you have in your data and can be actually quite significant. And and then you have to decide which one to use or what to do. Okay, in definition first, what do we mean by bottom hole pressure? It's you see here the abbreviation. The symbol we use is a small p, and subscript we use a WF, flowing bottom hole pressure. And is the pressure that we have at the top of the perforated interval. So actually we don't go inside here. We know that there will be a variation, might be a variation of pressure. There will be different rates coming in from the formation, but we define that as our bottom hole pressure by convention. And that is, different reasons, but essentially we have usually a lot of uncertainty what happens along the lateral, along the formation. How is the influx, if it's uniform or not? We might have heterogeneity, we might have all kind of strange things happening. So then the kind of the healthiest is, if you don't know all the rest, you kind of, that's like the point where you have less uncertainty. Okay, yeah, and that's okay, the deepest, if you want to make it formal, is the lowest point in the well where you can get the full mass flow or the full production is there at that point. So you have already taken all the contribution along throughout the whole section. Okay. Yeah, that's kind of expanding on what I was saying before, that you don't make it, to make it, if you want to progress further, you want to see how that pressure is changing in this section. Well, you need to have some idea of how much is flowing in, and for that you usually need some sort of IPR. Okay, you divide this in sections, and you specify different IPRs for each, and then you're trying to estimate how much rate you have. Okay. So in the interface, it looks something like this. First, you will see we're going to, in the exercises, I will show you how to do it, but you get a window in which you have well data. And the first part is well deviation survey. You have to add the MD and TVD point pairs. But then here at the top, you see top perforation, measure depth, and you see bottom perforation measure depth. Okay, so that will be 7958. That will be the point at where you calculate the bottom hole pressure. Okay, but if by any reason you make it here, okay, you make it at the bottom perforation, then it will assume that all the fluid is coming through here. Okay, that can also be done, but you're assuming like all the fluid is coming suddenly from the toe, at the toe. Okay, that's the depth at which bottom hole pressure is calculated. Okay, and I can have, of course, a deeper section, but that won't be taken into account for the calculation. Okay, so I don't think I have to go much into to this section, but essentially, why do we need to calculate? Essentially, we don't measure it. We don't have it available. We don't have a gauge that we might have some wells in which we have a gauge, but the gauge usually is not at the same at the formation depth. But we might have it at a different depth, or we have simply a well we want to make it cheap and we don't have the means to have a gauge there, or simply we had a gauge and then it got damaged after some time. Okay, so then it's not available, and it's actually very important for us to have it. Okay, we use it for many different analyses. For the platform Whitson Plus, we use it for all of these analyses. DCA, flowing material balance, we use it for analytical RTA, numerical RTA, numerical model. We use it for nodal analysis or diagnostics. We have multiple uses for that. So what do we use as an input to this BHP calculation? We use essentially we have a pressure at the top. Depending how it is producing, that pressure could be wellhead pressure or tubing head pressure or casing head pressure. And we also need to have the rates that are flowing, and those rates should be at standard conditions of oil, water, and gas. And we also need temperature, usually. Okay, what is the temperature of the fluid at that point? And then what we are going to do is we're going to progress from that point, from that top point with those rates, and we're going to calculate, taking into account the pressure drop you have in the conduit, we are going to calculate the pressure and temperature along the well. Again, to do that calculation, you need to have like a wellbore trajectory, a profile, which is essentially that point pairs that I mentioned before, measured depth and true vertical depth. And you need also to have, where is the formation, the top of the formation, okay, top and bottom perforation. We also need to have some idea about the geometry. And there we have essentially all the strings that we have inside, casing and tubing. So we need to know the inner diameter. That's essentially the flow is going through that, or if it's flowing through the tubing, for example, it's flowing through the inner diameter. That's the conduit that is bounding the fluid. Or we can also have it through the annular, and then it becomes important to have the inner, for example, of the production casing, and then the outer of the production tubing. Again, and for that, that's why we ask to the user to input that data. Roughness, we also need that. That's important for friction pressure drop. And we need also, the different end of tubing and end of casing depth. Where is it ending? Okay, to know how long the section should be. Yeah, one thing that I didn't mention here, but it will be important later, for some artificial lift methods, we actually need to have a, for example, for rod pump, we need to have the liquid level input as well. And for gas lift, we also need the gas lift rate. And for example, for ESP, we need to have the suction pressure value. Okay, that comes from like the sensor, the suction pressure sensor of the ESP. So for some artificial lift methods, that's not the whole picture, but actually we need some more data but that will be specific to the artificial lift method. Okay, so so that's the input that you need, and then correlations that we are using. That's essentially how we are calculating. We are progressing from the top, and we are moving downwards to calculate that pressure. We usually use some. Let me just put the full slide. We usually so in the general case, you have three phases. You have gas, oil, and water, and these amounts are changing along the tubing or along the well, because you are, for example, in the case initially you are entering with a lot of oil, and then the pressure is going down, temperature is going down, then gas is coming out of solution from the oil. So these amounts are going to change, and then you have to calculate, so essentially the pressure drop, considering this complex configuration. And I mean, it might be very, so exhibit different ways they are arranged, which are called flow patterns. Here you see that they are like layered, but they might be like one becomes droplets in the gas, or the gas becomes bubbles into the liquid, and this becomes like some sort of an emulsion. So you can have a kind of very complex and crazy stuff. But essentially, how we do the calculation, first we assume, and it's usually a good assumption, unless you have like emulsions, but you assume that the liquid, it becomes one phase with equivalent properties, with equivalent density and viscosity. And then you end up with a gas and a liquid phase. And then with those, you follow a similar procedure that what you follow in for when you have a for example, water flow, just liquid flow, a similar approach, but then you have to calculate some equivalent properties of that fluid. So it's like an equivalent fluid, equivalent density, equivalent viscosity, and there are different ways to calculate the pressure drop terms. And that averaging, it's kind of correlation dependent. Depending which method you use, the ones that we showed before, Bex and Brill, Hagedorn and Brown, they will have different methods to go from this configuration to this way. And here you can actually calculate the dP along the pipe. Okay, so these are correlations. We call them correlations because essentially they are first assuming you're doing that averaging. So you are kind of the gas and the liquid, you are trying to combine them in a way that they form like an equivalent fluid. And the other thing is that they are using data that was usually gathered in the lab. So in the lab, they run tests in usually in small pipe size, and then from there they generate some sort of trend correlation, sometimes quite smart, the way to gather all the data and make it it's a lot of parameters you have to change, so they find a way to try to put all of those parameters into one main parameter, usually dimensionless, and then try to do the correlation development with that. Okay, so you see here the ones that are available now in Whitson Plus. It's very classical correlations, Hagedorn and Brown from 65, Bex and Brill from 73, Gray from 78, and this one, which is this was actually a hold-up correlation. We will see later what is hold-up, but essentially that's a bit newer, and they was taking a lot of data from different configurations. The main thing that distinguishes these works, it's essentially what kind of fluids you're using. So what liquid and gas content, and the inclination angle and the size of the pipe. Essentially, they were developed using different different data. Okay. We also have some more complex models that are not available currently in the software. It's using mechanistic models that they trying to have a guess of how the fluid is configured, how the gas and liquid are arranged in the pipe, maybe if it's layered or if it's bubbles. So then you can actually apply a more complicated model other than doing this averaging. Okay, you can simply try to apply equations on the liquid and the gas phase and try to essentially solve it simultaneously. It's supposed to be more predictive, but really it's many times these reflux models or these correlations, how we call it here, they are like usually for engineering purposes quite good. They become mechanistic models become more relevant when you have, for example, flow assurance and you have complex transients that you want to solve. Actually, they are in those cases there are some benefits of using mechanistic models. Okay, but essentially you apply equations for each phase usually, and then you try to remove a bit the how do you call it, the empirical component in the equations. Okay, so that's how it looks like if you can relate it to like single phase flow. So you have, let's say, flow of water or oil in a pipe or gas in a pipe. You have, this is the pressure difference. Hello? Someone has a mic on. Yeah, so you have the pressure difference. They call it this the pressure gradient, and this is the position in the pipe. So it tells you essentially how quickly the pressure is changing along the pipe, and this S is along the pipe. So it's actually oriented with the pipe. This is a pipe length that is using the same angle as the pipe. And then we have three components. So that consists of three components. One is gravity. Okay, that is simply due to the density of the fluids, and we will see soon that this has actually the biggest impact locally. And then we have friction that's caused by the slipping of the fluid on the pipe wall, that you have a shear stress caused by the fluid. And then the last one we have is acceleration, and that's usually very small. We include it because it's simply to include it to make it full, but usually it's very small. It's relevant usually when you have high velocity gas flow. Okay, and that has to do with the change in kinetic energy. This is a change in potential energy in elevation. This is in the change of velocity. The fluid is going faster, so then part of the energy goes into increasing the speed, the velocity, and this is kind of the shear stress part. Okay, so if we are going to try to see how those components are, or how big they are, how relevant they are in a well. So you could see, let's say, look at this point here. We are in a relatively horizontal section or near horizontal section and close to the formation. So it might look something like this. A lot of the pressure drop is actually friction. A little bit, almost nothing, is due to gravity, and acceleration is, so again, almost nothing. But when you start entering into the vertical part or the more inclined section of the wellbore, the situation changes and you might have something more like that. Okay, that's kind of a very typical pressure profile. Okay, you have a lot of it is due to the gravity term, and then a little bit, let's say maybe 10-20% due to friction, and then very small part due to acceleration. And then when you move to the top, what happens at the top is that you have usually higher velocities, you have more higher shear, and then the friction becomes a bit bigger. Okay, but not that significantly. If we can do this, becomes a bit bigger. Now we can look at that just looking at how the gradient looks like at different positions, but we can also look at how the gradient in total is. If you look at the whole well and you take into account how much, when you circulate from here to there, so how much was due to gravity, how much was due to friction, how much was due to acceleration, and usually the picture looks like that. Okay, for let's say an oil, medium to low GOR, it should look like this. Okay. Okay, most of it is gravity, and then the rest is friction. If you have a gas well or a high GR well, then it might look more like that. Okay, then the frictional part, let's see if you can see the difference. Okay, the frictional part and the acceleration becomes a bit more relevant, but still the gravity has a kind of a big role. So all this is to say that on that equation that I showed you before, the gravity term, if you get it correctly, that's the key point, to get that element correctly, because the others are important but are usually less important. So most of the improvement in multi-phase flow modeling is actually to get that gravity term correctly. Okay, here it's just simply a sanity check we have. If we have a single phase flow, let's say water or gas, we see that all the correlations, they overlap. They predict you essentially the same bottom hole pressure. And that's because what distinguish the correlations is how they handle multi-phase flow, this averaging process. Okay, but if you use a single phase flow, then all of them should give you the same number, because they are not using this essentially this averaging method. Okay, so that's the equation actually is a bit different, because the acceleration, we are using a technique by Bex and Briel that actually they try to convert the term of acceleration into, they kind of make some manipulation of the equation, and then at the end they end up with something like that. Just to make it more elegant and get rid of this. If we go back a little bit, I can show you here. Okay, to get rid of this dVds, they make it in terms of dPds, and then they can kind of make the equation a bit nicer to handle. And I think that the first one that was doing that was Bex, and in the paper of Bex and Brill. Okay, so you have, as I mentioned, this is the gravity term, and getting that density is actually very, very important. The average density, that's really the key part. And then you have multi-phase friction factor, that's also important. Friction density, if it's different than that one. And then you also have an acceleration density there. Okay, remember that's due to elevation change and the density of the fluids. This is due to the shear of the fluid with the pipe, and this is due to the kinetic energy change. Simply it's flowing faster, and then part of the energy is converted to kinetic energy. To calculate this density due to gravity, we usually equivalent density. We usually need something called the holdup. Liquid holdup. If you have, let's say, a fluid gas here is this is in color red, and the liquid is in blue color, so it might have a configuration like that. Okay, in an inclined section. So if you make a cut here in the cross section, and you might see this. Let's say you make the cut here. Okay, you might see this distribution. This all of this is occupied by liquid in the cross section, and this is occupied by gas. So the holdup is going to be the area of the liquid divided by the total area, by the area of the pipe. Okay, why that's important? Because we calculate the density, equivalent density, usually with that holdup. We take the density of the liquid times the holdup of the liquid, and we take the 1 minus the holdup of the liquid times the density of the gas to calculate that density. So if we get that number correctly, we're going to get that density correct, and then we're going to get this term quite accurately. Okay, and just I want to also kind of call to your attention maybe something that it's a bit more advanced, but essentially this holdup, if I said, well, I cut here and then I see this cross section, and that will be my holdup, but actually that's something that will change with time. So here is a very nice animation from this is a research institute in Germany, and it shows you like essentially there has bubbles come. In this case, we're looking at if the fluid is arranged in bubble. This is called like bubbly flow. You see that there will be bubbles that come and go. Okay, so you have actually points in time in which you have no gas, and then suddenly you have a bubble of gas, and then nothing, and so forth. What you do is that essentially you integrate what we are looking at here. This is like the integrated in time. We let some time pass, and then that's like the average in time and space, because we are also averaging in the cross section. That will be what we say it's a liquid holdup. Okay, let me see if here I don't get the it doesn't take that long. We can let it run. Multi-phase flow is very complex. It's essentially not steady state. If you pick a point inside the pipe, it will be changing all the time with time. But by using that, we are predicting average properties in time and space. Actually, we can develop methods that are quite accurate, and for engineering purposes, they are quite acceptable. Okay, so you do it, let it run for some time, and then you do the average, and that's kind of the value that you report. Taking a bit longer than I thought. Okay, take all you do an integration of all of those, and then tells you what this is liquid holdup, but we also have something called, we can call it gas holdup. Is the same, so it's the amount of in the cross section if how much is occupied by gas, the area that is occupied by gas, and but it's more correctly to call it void fraction. Void fraction because there is something missing, and that something missing essentially people refer to as a gas. But yeah, all of them refer to the same thing. Okay, so we have these 4 correlations, and we usually the question we get often is which one is the most accurate or which one should we use? And that was actually the focus of recent, I think it was JIP that is reported on this paper. And there was many wells that had available gauge pressure, and then you had the correlation to estimate the pressure at some location in the well. And there were 420 wells, and you have many measurements along time, so more than 300,000 points. And these were for different basins in the US. So actually that's reported there in this paper, but I'm going to cover some results here. So these are for the different, you have different plots of the different correlations, and this is the absolute error that you have between the correlation output and the gauge, the actual value that you measure. And this is showing how many wells you have that have that amount of error. Okay, so for example, here you see that the highest error for Bexambril negative was minus 1000 psi. Okay, but there were not many wells actually that had such a high error. Okay, but you have quite a few more that had errors all the way to 200 psi. Okay, then you had maybe a lot that had errors all the way to 400 psi, and then you have quite a few that had errors above 400 psi all the way to 1000 psi. So that's what this chart is telling you. And then you see the same for the different correlations. So Hagedorn and Brown, you have a very few that have errors all the way to minus 800 psi, but then you have some more, okay, and so forth. But we are going to compare them. I have another chart that I think hopefully is better, but what we're using to compare here is the median error, which is the average of the highest error and the lowest error. Okay, so you see here the median for Bexambril lies on 201 psi. For Hagedorn and Brown, it's minus 63 psi. For the Semayat and Gajar, it's 60 psi, and for Grace, minus 128 psi. And the sign tells you essentially that like these two are under predicting usually, like you are kind of under predicting the actual value of pressure, and these are over predicting. Okay, that's essentially what it tells you. If you want to make it in terms of absolute error, okay, you have here that is 80% to 100%. Actually, you completely missed the value. Okay, but essentially these are the same results, and you see that in terms of median error, actually the best are Hagedorn and Brown and Semayat and Gajar. They are quite similar. Okay, one is under predicting and the other is over predicting. Here it's another chart. I'm sorry, this is the one you don't have. I just made it this morning. I thought hopefully this is a bit, it can be used a bit better to explain what the findings. Okay, so here on the x-axis, you see several buckets. These are points for which I had 0 to 10% error. Here you had 10 to 20% error. This is relative error and is the absolute value of the relative error. Okay, so like in this chart, we distinguish between if it's minus or plus. Here we don't distinguish. Here we say that every error, if it's plus or minus 20 to 30%, is going to be into that bucket. Okay, and all the way to 100. And here we have the percentage of data points that fall into that bucket. Okay, and we have the colors tell you the different correlations. Okay, so for example, for Bexambril, you see that 27% of all the data points fall in the 0 to 10% error bucket. Okay? Then you go to the 10 to 20%, around 31 of the points fall into that bucket, and so forth. Okay. So here you see a big difference between, so Bexambril, it has 27% of the data points fall into these buckets, 0 to 10%. But you see Hagedorn and Brown and the Semayat and Gajard, they actually have all close to 50%. So they were able, those correlations were able to predict with more accuracy, more points within the 0 to 10% range. Okay? In the 10 to 20% range, we're like quite similar. but then in the 20 to 30% range, they were actually more. So it was more from points from Bex-and-Brill and Gray than the other two, and the trend kind of continues for higher error values. Okay. So it tells you essentially that it seems that which is similar to this conclusion using the median error, that these are more accurate, essentially. These are more accurate, the more points fall into the lower error bucket. Okay, let's put it in a different term, is if you use Bex-and-Brill, 78% of the points had a relative error within plus minus 30%. Using these two is close to 90% of the points are close to 30%. So it's quite good. Quite a lot of the points actually fall within the plus minus 30% range. And if you use Gray, it's someplace in between, but closer to Bex-and-Brill, 82%. Here is another plot showing the how is, because here we are kind of grouping all the wells, and we don't know if there might be some GORs or some conditions for which we have higher error than others. Okay, so here we're trying to look at the GOR on the x-axis, and then this median relative error for each GOR value. Okay, and we see that for very low GORs and for very high GORs, actually this mean relative error is kind of shooting, is kind of decreasing in this case. Okay, for Bex-and-Brill, it's usually quite high at 15%, but then it's kind of reduced on the extremes. Okay, and the same thing you can see for the rest. Okay. This don't take. So what happens here at the end? We should take it with a grain of salt, because usually for those wells with high GOR, they don't have usually gauges. So that's, you see here the number of wells we have for low GORs, which are oil producing. They are kind of, they can afford essentially to have a gauge, while the others, they it's too expensive usually. Okay, so the sample size is not, here you see that you have very few wells, which might be, tens of wells, while here we have more like in the range of tens or hundreds. Okay, so our recommendation based on that study is to always try to look at all of them, the 4 correlations, and if you have gauge data, even if it's not for the same well, but you have some well in the vicinity that has gauge, just try to compare against gauge, and then based on that you use the one that is the closest. If you don't have any of that, you're unlucky. You're in a region where you don't have any gauge, you don't have any neighboring well, you don't have any previous experience, so use this well, the Semayat and Gajar, okay, which gives the same, similar to Hagedorn and Brown, but is this correlation, the good thing is that it's developed using more inclination and more data, so it should be more general. And the idea is to expand this study in the future, to run another project and try to see if this holds for other cases and other fields. But essentially, that's what they found in this paper. Okay, now let's talk about flow path. So that means how the fluid goes from bottom to top, and that's important because that's the path that you're going to follow to make your pressure drop calculations. Okay, so these are all the paths that you can follow. Here you see, we'll see again, this is the same window actually that I showed you earlier when you put the deviation survey of the well. But now you have a second step in which you add, like, essentially is the completion data. So what is the completion of the well? And here you see you can have all of these options. You can have casing, flow in the casing, flow in the tubing, flow in the annulus, flow in both. You can simply use the gauge value. Don't use any, don't perform any calculation. Use the gauge value. And you can also say unknown. And we are going to go through all the options just that we can clarify what is each. Okay, but essentially you have this window, well data. You can put as many configurations as you want. They will be applicable from the time that you specify here. There will be a time tag, and then you can specify like how is the flow for each configuration. Okay, you have to provide the casing data and the tubing data, and then you specify, yeah, how is the flow. Okay, this is the same that I showed before. Okay, flow path casing, very simple. You have two options. Either I have the, in this case will be, yeah, the casing or the top pressure, and then I have the flow rate, and then I go down and calculate the top of perforation pressure down here. Or if I have a gauge value, let's say I have a gauge and that gauge is not at the top of perforation location, then I can say that just run the calculation not from the top, but run it just from that point and below. Okay, sometimes that's desired, especially, we are doing is like an integration procedure. We're calculating pressure, first dividing in steps. So we take the path into, let's say, I don't know, 50 meters or something steps. Okay, and then we're calculating pressure here. What is the pressure 50 meters below, and 50 meters below, and so forth, and 50 meters below. So if the correlation is not very accurate, that error is going to compound, is going to add up. Okay, and at the end, maybe you're going to end up having a big error here. Okay, but if you have a gauge, you have a pressure point at some lower point, a deeper point, so then you can do the calculation from there. And if the correlation might not be very accurate, but then the spread will be less because of that, because you're integrating over like less steps or less intervals. Mm. Then tubing path, I have a production tubing installed, and then I can decide if to, again, the same thing as before. I can flow through the tubing, and in this case, you can have flow in the tubing. Usually doesn't go all the way to the top of the perforation, so you might have flow in the tubing and then flow in the production casing. Okay, or if you have a liner. And if you have a gauge, can also do the same. If you have the tubing, you have at some place you have a gauge, so then that will take it as a top pressure, and then from there we'll integrate down to the top of perforation. Okay, annulus, it's producing through this section, through this essentially is assuming two concentric cylinders and flowing through there. And so first you do a calculation in the annulus, and then you do a calculation in the production casing. Okay. And here the same thing. If you have a gauge at some position, at some location, then you can do the calculation from gauge and down. So all of them have the option to calculate from gauge, not from top pressure, but from gauge, if you're lucky enough to have the gauge. Parallel flow, sometimes this is used if you don't have a production packer that isolates both. You produce through both. Essentially, that gives you, if it's a high rate well and you don't want to change the tubing, you don't want to make an intervention, you could produce in theory through the two, both of them. And I think there are some clients that are producing like this. Okay. And here it's a bit of so all of these are kind of straightforward. You provide the top pressure, you provide the rates, and then you calculate to this bottom point. But for this one, you have to do some iteration. You have to do some guessing. Okay. You have to, because usually you don't have the rates through each one of these two, but you have the commingled rate. So you have to make a guess of how much is flowing through the annulus and how much is flowing through the tubing. So then you make an assumption, let's say 50-50 initially, and then you have that pressure, tubing head pressure, casing head pressure. You go down and you calculate this pressure at the end of tubing should be the same. If it's not the same, that means that the guess you had, 50-50, is not correct. And then you have to change to something else. You have to change to maybe 40-60. Run again, check if they are the same, no, and so forth. You repeat. Quite a heavy, computationally expensive process, but then at the end you find that pressure, common pressure, that will be the same for both, and then there you can proceed to the top perforation. Okay, so this is a bit special because it requires iteration, because usually the split is not known. You don't know how much is flowing through the annulus and how much is flowing through the tubing. Measure BHP, that was one of the options we have on that list, and essentially that's simply you thrust in the gauge, and the gauge is close enough to the top perforation that or the top of the formation, so you use that value. If it's unknown, this it's actually, you say, well, why this guys have this crazy option. It's simply sometimes you don't know. Like you have to go to the wells and you have to find out what has been done in the wells so to see what is happening there. And we have this logic that is, if you don't know what kind of flow you have in your well, you can say if the tubing, the casing head pressure is greater than the tubing, then the flow will be through the tubing. And of course, if you have a tubing, then the flow will be through the tubing. But if the tubing pressure is less than the casing, um, um, yeah. So if the pressure here is lower, then it will flow through the tubing. If the pressure here is lower, it will flow through the casing. Okay, and through the annulus. Okay, and if there is no tubing, simply you flow through the casing. It has some logic that has been helpful for some clients. Yeah. Here you see this more detailed. If P casing is less than the P tubing, then okay, this pressure is lower than that pressure, then simply it goes always through the flow path that has the lowest pressure, the lowest top pressure. Yeah. Then there is some nomenclature also. So if you have rates and you have top pressure, that's what is typically done. But you can also choose to perform quiet side calculations. And that means the quiet side is a side through which you don't have any flow. Okay, so for example, if you're producing through the tubing, the quiet side will be the annulus here. And then you can actually do an estimation of that pressure by taking that might be a stagnant column of gas. Okay, usually you assume that it's all the way to the end of tubing. And then you calculate from there, you have that pressure and you calculate from there and the rate, you calculate what is the pressure at the top of formation. Okay. So instead of going through the tubing, with that tubing head pressure down to end of tubing and then flow through the production casing. So then you flow from the casing head pressure, assuming a static column of gas, and then you reach the end of tubing, and then from end of tubing you calculate, and that will give you a different, of course, can give you a different number because you don't know exactly where is the liquid level here, right? Or what exactly is filling the annulus. Okay, here is the quiet side in gas lift. In gas lift, you do the same, but now the fluid is moving. So then you have to, it's not only a hydrostatic column of gas, but now you have to take into account the friction drop. So you go from casing head pressure, taking into account the friction drop all the way to allocation that you specified, can be one of the valves. And then from there, you move down using flowing the tubing and then flowing the production casing. Very useful for many cases to have this quiet side calculation, but it's a bit difficult to understand what it is. Okay, flowing, essentially that's the default. We go through the flowing side, follow all the time what we have when we have fluid in movement. And this quiet side is if we have an annulus where we have some stagnant or we have some parallel path to the tubing or casing. So then we follow that path and then we continue from there. As deep as we can get, and then we go to the top of formation. Yeah. Artificial lift methods that are in the software. This again in the same screen where you specify the well completion. Then you have these artificial lift methods, and these are all the methods that are available. None, simply natural flow. Gas lift, we're injecting gas either through the annulus or through the tubing, and then we're producing through the annulus. We have an electric submersible pump. We can have a rod pump, or we also have a plunger lift. These are kind of all the options that we have. Gas lift, there are 3 configurations. Something that we call poor boy. It's simply you have no valves. Everything will be assumed to be injected at the end of tubing. So then you also don't have a bottom packer. Valves is that you specify at which depth you want to perform the injection, or you provide also the pressure surface open and pressure surface close of the valve for the software to find out through which valve are you injecting. Okay, and automatic, we are going to go through that option later, but essentially it's going to calculate automatically with the values that you provided where it thinks it should be the injection point. If you don't know, let's say you haven't gathered, it's difficult, it's not yet, you don't have information available where the valves are located. Okay, this is the pour buoy configuration. You're injecting at the bottom of tubing, and then it's commingled. So you have essentially two paths here. You will perform a calculation with the gas lift rate and the formation rates, oil, gas, and water. And from this point down, you're going to perform a calculation only with the formation rates only. Yeah. And if you use the reverse gas lift, in which you are injecting through the tubing and producing through the annulus, it's the same. Essentially, you're calculating from casing head pressure, assuming formation fluids and gas lift gas all the way to the end of tubing, and then from there, end of tubing, you calculate the top formation pressure using just the formation fluids. That is, if you have valves, you specify that you have at some depth, you have valves. Typically, we have these valves for unloading purposes. So typically, usually gas lift is more efficient if we inject as deep as we can, because most of the column, a big chunk of the column will be, you will have a lot of gas, and that density, effective density, will be closer to the gas. But if we want to do that without any other valve installed, then we will have to have a very high casing head pressure. We will need to have a very injection pressure here, surface injection pressure at the top. So then we use an arrangement of valves at different depth such that I can start injecting through the one that is shallowest during the startup process. And then that one will close, and then the next one will open, and then it will close when the pressure has reduced enough, and then you enter into hopefully the last one. Okay, but the software doesn't assume you inject through the last one, but it will find actually with the values that you provided which one is the most likely to be open, and that's the one that we'll use, because it's not guaranteed that you always reach the deepest one, although that's what you will want to aim for in reality. Yeah, and here is a reverse is the same. Essentially, we inject through the annulus, the other we inject through the tubing, but we have gas lift valves in the tubing installed, and then we decide through which one, we find out through which one you're injecting. Okay, sorry, it's a lot of information, but hopefully when we go through the exercises, you kind of understand all the options. Here is like giving you a basics of artificial lift and what options you can find in the software. Yeah, an automatic, this is finding by itself with the values that you provided what is the injection point. And it might be that you don't have a valve at that location, but if your system was well designed, most likely that's where you have your valve, even though it's not reported. Okay, so you essentially you compare pressures in the annulars and in the tubing, and then when both are equal, that's the point where you should be injecting. At that point, you simply to pressure equilibrium both. That's the point of injection, and that's the point that you use. And yeah, if you then go and find out in your well that where you have the valve usually should be at a depth that should be close to that. Another artificial lift method is a rod pump. Rod pumping, we rely on the liquid level that is measured, that you have regular measurement of liquid level, maybe with an air gun or something similar. And then that also should be input into the software. Okay, that also should be an input in the production data. So we measure that liquid level. We might have flow through the annulus because we usually in these rod pumps we don't want them to handle gas, so there is a gas diverter at the suction. So the gas usually flows through here, kind of bubbles through the column of liquid, and then goes from the surface of the liquid and to the kind of at the top. So then taking only into account gas, usually here we have is very lean or very kind of single phase flow gas, we calculate from casing head pressure to liquid level. We calculate that pressure, assuming, considering the gravity and friction. Then from here at the liquid level, then we calculate end of tubing or the pump suction. And that can be, we are considering there the flow of the gas through the liquid, because that column might not be pure of liquid, but it will have some gas flowing through it. So that affects the density of that column. Okay, if you think of it, if we had like, let's say, I don't know, 1,000 feet column, okay, it's different if we have it full only with dead oil, or if we have gas through it. The gas will occupy part of the cross section, and then the density will be less than that pure oil density. And then after we calculate the pressure there at the end of tubing, then we can have the formation fluids and that pressure, and then we calculate what is the pressure at the top of the formation. ESP, electric submersible pump. We depend on the suction pressure. Usually these pumps, they have a cable, and in the cable they record all kind of information. But one of that, usually they have a pressure sensor measuring the suction pressure. So that should be input into the software as part of the production data. And then you calculate from that point and down using the formation rates. Okay, that's essentially how ESP is working. Okay, so when you select here artificial lift method ESP, then you have to provide the gauge step, and you have to give a gauge value, depth value. Okay, and that becomes automatically selected. Okay, you're not neglecting everything else that happens, because you already have this pressure, which is quite close to the formation. You want to use that. There is less uncertainty, and then you move from there and down. Plunger lift. Plunger lift is a bit tricky. It's essentially we are operating the well in a cyclic manner. So we are, letting the plunger down. We are letting the pressure accumulate, and then the plunger goes up, pushes all the liquid out of the well, and then we let it produce for some time, and then we repeat. We drop the plunger, goes down, and then the liquid accumulates again, the pressure accumulates again, and then we use the plunger to push the liquid out of the well. So what the approach here is to model that is that you should use so the average, the well won't be producing for, let's say, a full day continuously, but it's going to be producing only through the producing cycles. So that's the rate that you should use. You take all the volumes that were produced in a day, let's say, but then you see like divide by all the active producing time. So those are the rates that you should use to get like bottom hole pressure that makes sense. Okay. Otherwise, if you have a liquid level measurement, sometimes this plunger lift, if you have no bottom packer, we typically do that too, because then you store some. So when the pressure is building up, if you have the bottom packer, then you only depend on the volume of the formation, and that might not be, it might take a while to fill up. So what some people do is that they use also the annulus as a lung, some sort of an additional volume. Okay, and then that's increasing, and then when they let it flow up the plunger, then all of the gas accumulated here is going to flow up. But if it's the case that you have no bottom packer, you have like an open annulus, so then you can, and you have a liquid level measurement, so then you can do the same calculation as for rod pump. Okay, you have a liquid level, you calculate gas column, and then a liquid column, and then you move to the bottom perforation, to the top of the formation. This is a new, relatively new feature that if you have, for early stages, you want to estimate initial reservoir pressure. I will let you the animation run first. Okay, initial flow, then you have the bottom hole pressure, and you know that if it's very close to each other, the reservoir pressure shouldn't have changed that much, should have been at least quite close to constant or to the initial value. So then you can use this tool. You calculate bottom hole pressures and you use this tool here to estimate initial reservoir pressure using you're fitting essentially an IPR. You are saying that all the pair points of rate and bottom hole pressure should fall on one line. Here we are using Vogel. We can use you also use the back pressure equation, and then from there we extrapolate all the way to zero rate, and that's like the initial reservoir pressure. Here you have a link if you want to read more. It's not the main focus of this course, but if you want to check it out, so you see how to do it. Okay, very useful for like having a rough idea of initial reservoir pressure if you have some initial production data. Okay, of course, for doing that, for them to fall on the same IPR, the reservoir pressure shouldn't have changed that much. Okay, so you should use, if you let it, don't use points that are, let's say, month away or a lot of days away. If you try to use points which are, hours or days within the month, that is better. Otherwise, the reservoir pressure starts to drop, and then it's not that they should fall on the same line. Yeah. Now, all of these calculations, you see here, one problem is that they're going to be very spiky, and that is for all kind of reasons, but essentially the input is changing a lot. Rates of oil, gas, and water, and the pressures are also changing a lot, so then we get a very spiky behavior. So there is a functionality in the software, because you don't want to usually use it like that for any of your other workflows, because then it can create issues. It's essentially might be an artificial behavior. Okay, you want to have it a bit smooth. So this feature, we're going to go through it in one exercise, is to smooth the trace, the output that you get from the bottom hole pressure calculator, and then you can use that smooth traced. Okay, and you can choose the one that you want to use as a base. Okay, here is the measure of the gauge, but then you can use, for example, the output of Bexenbriel and do the smoothing. Okay, and to go through that a bit later. Okay, so gauge pressure, typically in this case, we have an example in which they're very smooth. You have just one spike here, but when you calculate bottom hole pressure using these correlations, they're going to be quite spiky. Okay, so that helps. This smoothing helps to at least have a nicer trend, and then don't have so much, a small variation that at the end is not that important. Okay. Another feature that the software has is correlation tuning. So many cases, often cases, it's not going to match exactly. So some people want it to match it perfectly. Okay, and then they want to use that match for other wells, or they want to use that match into the future. And if that's something that you want to do, you can do it in the software. You have your tuning essentially on that equation of dPds, or pressure gradient. You're tuning, adding two constants, one for the friction part, one for the gravity part, and then you're changing them until you get a good match, okay, with all the production data. Use it carefully, because you're changing a bit the physics, okay? You're trying to give more importance to some, let's say, some importance to that might not have. Okay, so just use it, with very carefully. Okay, this tuning, like any tuning we make, just use it very carefully. You'll always verify if you have any data that it matches properly. Better, I think, is before doing any tuning, to see how is the spread of the different correlations. You have 4 of them, and see what is your gauge value, and see if how close they are, and if might not be perfect the match, but if it's within 20-15%, I will consider myself quite happy with that match. Yeah, with this we cannot do with an ESP, because in the ESP the pressure value we have is available at the suction of the pump, and we so to verify, let's say that the calculations are correct, we perform calculations from the top to some location into the tubing, and then we compare against a calculated value, a measure value. Okay, but in this case, the measure value is upstream the pump. We usually, I don't think there, at least it's not recorded, it's not reported the pressure at the discharge of the pump. Okay, so I cannot do the tuning because I will be tuning without considering the pump, which will be wrong. Okay, so don't do the tuning with ESP because there is the pump is in the middle. Okay, and essentially I will be tuning a wrong value. Okay, I will be tuning a value that's supposed to be there and but is in reality is there. Okay. Okay. For more information, that's how much we're going to go into the the theory and the options in the software. Now comes the exercises. So if you want to know more, you go to the wiki, and there is quite detailed. It's quite nice, the explanations that the guys have prepared about how the details about how the calculations are performed and what correlation and what options. You can read there more details. So now I think we reached the exercises, and I think it's good if we take a little break. I think we already running for 1 hour, so we can take let's say 5-minute break, and then we come back with the exercises. Before we maybe to give you some time to on the 5 minutes, if you don't want to be idle, you don't have still you don't want to drink anything or go to the toilet. This is what we are going to cover. We are going to cover first a gas lift well, and we're going to look into all of these options. Injection at the end of tubing. We are providing valves, location and opening and closing pressures, automatic. We will cover the smoothing functionality. Rod pump, electric submersible pump, liquid loading. We haven't discussed liquid loading in the theory, but and then a tuning exercise, and then using mass upload. Just a reminder, you should have access now. All of you that are in the call, you should have access to this website. Remember, don't use your corporate domain. Okay, use this one because otherwise you won't find the information there in your corporate domain. Your username is your email that you use to register to this course, and also the password is like this. Okay, BHP all capital letters, Whitson all small letters, this number, and then don't forget the exclamation mark at the end. Okay, and just make sure that it works. If it doesn't work now during this break, we try, send a message to Mo. Okay, so see you in 5 minutes.
All right. Here to learn.
Hello, hello. Now we are back, and yes, I have to admit something. I'm not the most expert user of Whitson Plus, so I might get into trouble. Hopefully, Mo will be there to help me. But I think that I'm getting someone, and but I think what I tell my when I teach, I tell my students that it's good to have. I call it peer teaching. That is different if you get the teaching from an expert that already knows all the ins and outs of the software, and then they never make mistakes. But if they learn from a peer, they make mistakes, and then they try to find out together what did they mess up. And usually they learn much more in that way. So hopefully it will be true. Now I get to try if what I'm my preaching, my teaching, is actually true or not. Okay, let me see. Go back to the presentations. Okay, so if you go to the domain courses.whitson.com, you log in with your email and the password BHP Whitson 2025 exclamation mark, and then you go to fields. You should have only this field. In my case, I have like an administrative account, so I have many more others, but you should have just this one, BHP course 2025 within fields. And there you should have, again, just one project. That's simply the way it is arranged, fields and then project. And on my project, I will find mine. You will have just something like that with your email. And here you should check also that you have 5 wells, because these are the wells that we are going to be using. If you have 0, just also again give a message that they can fix it for you quickly. And you see the wells that are there. It's a gas lift that we will run this pour boy, the valves and automatic, and then the ESP, a rod pump, dry gas well, and BHP correlation tuning. Okay, so let's click on that gas lift well, and after you click on it, you see here at the top, just to make sure that you're on the right place, you see BHP course 2025, just your field. Then your project is your email, and then your well is a gas lift well. And if by any chance you're in the wrong place, you can use this to change. I think the error you can make is that you are not in the right well. Okay, because I think you have just one field and just one project. In my case, I have many more, but the main error you might have is that you're in the wrong well. Okay. And let's see first at the, so this is some general information about the well that you can populate if you have. If you don't have, location and other things that are important. But here you see to the right, what are things, analysis that have been performed in the well. So you have PVT data, you have production data, and you have some wellbore configuration that has been added. Yeah, and after that, you haven't performed almost anything, some DCA. But what we are going to be doing is that this guy now here is going to be, that will become green, because we are going to perform bottom hole pressure calculations. Okay, so let's first inspect the production data. We click here on the left, production data. It's got frozen for some reason. Remember, I'm in Norway, so to come here, the internet has to first go through the normal fiber and then has to take a donkey from the terminal here. So that's why it takes a bit longer time. Okay. Okay, so here you see the production data. And you see first here you see a plot where you see the rates of oil, gas, and water. You can, yeah, I think if you want to isolate, you can double click. Okay. Just if you want to see only one legend, but you see the oil is the green, gas is the red, and water is the blue. And then also you see the gas lift rate. This is this continuous line that is there. Okay, this blue, dark blue. Okay, and then you have also tubing pressure. This is this gray value there. And then you have the casing pressure, which is this continuous gray trace here. And here you have below, you have the data in table format. Okay, so you see that well was producing from the January 4th, 2021. And here you have no gas lift, no liquid level, no choke. But then you see here at some point you start having, at this time, February, you start having some gas lift injected. And here for some reason was missing. Okay, but then you can go down to the next page. And you see the gas lift was actually here increasing. Okay, so that's the data. So you can also see it in table format someplace there. Okay, so you can see all the data that is available. Just take my pages here. Okay, so let's now go to the bottom hole pressure. Is here on the left on the menu, bottom hole pressure, and you see here we have just the there is actually a gauge in this well, which is this solid black line. This is with time pressure, and we also have a tubing pressure, which is lower. Of course, we have flow from the gauge all the way to the tubing. That's why it should be lower. And then we also have the casing head pressure, and we have initial reservoir pressure here marked in this line. That's what this plot is showing. Okay, and so far we haven't done any calculation. You see here you go up in this. This tells you like the status of what has been done here in this module, and so far it tells you no calculation has been done yet. Again, this it tells you so far, because I haven't done any calculation, that the one that is the bottom hole pressure that it will be used in all other calculations in the software, in all the other modules, if you want to use it, then it will be simply the gauge. It will be this solid black line. So now let's go and look at the well data here. When we click on edit well data, we're going to get this window. And on that window, we have this we have to populate. I will do it here manually for you, but then all the other wells, they will have less information and less to populate until I think we simply use the file as it is. Okay, but just to give you an idea of if you do it through the interface, how it will look like. Okay, so I have if you have your slides, let me go back to the slides. Okay, on the slides, you have these values. Those are the ones that we are going to be using. Okay, we'll input them manually. A top perforation, bottom perforation, that's the location where my bottom hole pressure will be calculated. That's the deviation profile of the well, measured depth and true vertical depth. Yeah, and we have 4 points. So that's what I'm going to be inputting here. Okay, and then 18,400. I hope you can see well the numbers. I have a relatively big screen, so. Okay, and then here I have to add this deviation survey, which is 150, initially like a vertical section, short of 150 feet. Then I have, and then 7515 is complaining because I haven't put everything yet. And then to create one more row, I just click enter, and then it opens one more row. And then I input here 7600. Okay, so now it stopped complaining because well, the MD of the top perforation now it exists actually in the deviation survey. Okay, let me make sure that I didn't make any mistake. Also, you check your numbers. You know, probably you're in a bit of a younger generation than I am, so you can do it quicker. Okay, and okay, then I click here on this this icon that I have there, and just to visualize how it looks like. And that's how it looks like a very sharp vertical section, almost vertical with very low inclination, and then you have this horizontal part. That's what, you know, the perforated and fracked interval, most likely. Okay, so bottom hole pressure, it should be someplace there. Okay, someplace that will be the point where you have the all of your mass flow, all of the reservoir fluids are coming in. At that point, you don't have any more influx from the formation. Okay, then to move to the next one, you have to click here on well data, and that's where you put your completion information. Okay, you see here you can put as many configurations as you want. This plus will allow you to have, if you have, typically we do recompletion, we do side tracking, we do other things in the well, so we typically can add all of those there. Okay, but in this case we are going to have just one. We are going to have the natural flow first, and then we're going to have the gas lift configuration. Okay, or just the gas lift from the beginning. Okay, no natural flow. Okay, so I will take here casing information. We have first one. Let me see if I'm in the right place. Okay, so if we go back to the PowerPoint just to show you where we are. Okay, here. Okay, that's the data we have to input for casing. We have first one casing down to 7549 MD. Kind of a big casing, and then we have a smaller casing inside that has a 4276. Okay, and then tubing, we have tubing all the way down to 7325 with 1.9995. Okay, and here we have to select, yeah, that will come later, gas lift. Okay, so let's input that data here on the software. First, one casing string that will be all the way down to 7549. If I read this correctly. Then I add one more. Okay. The again from the top. Okay, this I'm assuming these strings are go all the way to the top. It doesn't really matter that much. It's only going to take what applies from a given MD. It will take that section. Okay, so that and here it's 18598. Okay, that's the end. That will be the toe. And here we have 4.276 and 0. The roughness we can actually copy from the top. We're going to use the same roughness, although it changes a little bit with diameter, but usually the change is very small, so it can be assumed kind of constant. If you don't want to, you also have the option to go to the catalog here, the casing, and then you find exactly what size you have. So usually it's with the weight and the OD, so you can find out exactly what size you have, and it will find the inner and outer diameter. Okay, in our case was 4.2676, so it's this one most likely, an 18 ppf. Yep. Okay, so two casing strings, one bigger, one smaller, and then below I have the tubing, or I have the tubing within above that, sorry, and then I have 7325 all the way down to 7325, and here I will find in the catalog there will be one that is 1.995. This one, okay, let me go back, I went too fast, but it's 4.6 ppf. Okay. 2 and 3/8 tubing. Okay, just to make it easy to populate, if you don't want to populate the numbers manually, but if you have something fancy, special, premium, then you can also fill it that it's not on the table. You can also fill it manually. Yep. And then here we say flow path. We're going to have flow path through the tubing. We're injecting gas through the annulus. So tubing, artificial lift. Here we're going to say gas lift. And the configuration we will use first is pour buoy. But we have, we already mentioned we have these three. Okay, we have reverse valves, we have valves, and we have automatic. Let's for now use injection. Remember, this is injection at the end of tubing. Okay, let me do one more check to make sure that the input is correct. I think like a lot of the errors we get when doing simulation is simply we don't spend too much time looking at quality controlling the input. And then we find a number that doesn't make sense. It's causing all the trouble. Okay, and then we simply click save. Okay, and now has that configuration stored from the beginning. And now I can actually calculate bottom hole pressures. Now we can make our first bottom hole pressure calculation. Let's see if I can. I think maybe the zoom is a bit too. Yep, maybe that's maybe too small. Okay, let me run the calculation. Okay, and you find something like that. Okay, you see here all the different colors. This blue is Bex and Brill. This red is Hagedorn and Brown. This green is the Semayat and Gajar, and gray is this violet color. Okay, and you see that actually these three, the last three, they kind of overlap quite closely. They are quite close to each other, but then Bex and Brill is a bit of an outlier. It's staying a bit out. And the gauge here, you see that there is actually a difference. Okay, but might be that the gauge location is actually not in the same place as the bottom hole, at top of perforation. Okay, that might be a reason why might be different. Okay. I hope all of you got it correctly. Most of you. If not, ask for help. Yeah, I don't think we have much more interesting to show here in this chart, unless I'm forgetting something. So now let's do the calculation. Now we are going to let's go back to the PowerPoint to see where we are. Okay, we are here is introducing the input. Here we are showing the catalog, and here we are specifying what kind of artificial lift method you have. And then we are going to look at, now we're going to use a more advanced method, which is using valves. Okay, now we are not assuming we're injecting at the bottom of the tubing, but now we actually know where we have our valves and what pressures do we have. If, let me see, I have here, it will look something like this. Okay, you have here, as part of the tubing string, you have some gas lift mandrels that are installed, or valves. And you have the depth at which they are installed, and then you have also the opening and closing pressures, and they will open at different. These are designed such that they are not open. Not all of them are open all the time, but they are open only during the unloading process until you reach the normal operation, and then hopefully the deepest one is the one that will be open. Okay, so these are what we are going to use. It's something similar to this, not as many. Just to make it simple, we're going to use only three. First, I think we're going to use just one, I think, at one depth. Okay. Let me see here. Okay, valves. Okay, we're going to add one valve at 7,000 feet. Okay, we go here you click there on this to get this screen with the deviation survey, and then you click again there to get the completion configuration. And here you say, here we're going to change from pour buoy which is end of tubing, all the way to valves. And here it opens this screen. And now I can put a valve at 7,000. Okay, and if it's only one, that will be the point at which it's going to inject. And you see 7,000 is actually quite close to the end of tubing. Okay, end of tubing is 7,325. So it might be here that I have actually a bottom packer, but then I have a valve, and that valve actually doesn't have any opening or closing pressure, but it's essentially an orifice. So it's always going to be open. And that's from where that's where I'm injecting all the gas. Okay, then I click save. And here is something interesting that the software tells you. Here you see this warning, very, very soft, but at the same time, very, it's very, it tells you that this calculation hasn't been run because there was a change in the configuration. Okay, I changed the gas lift data from poor boy to something else, and now the results that are shown here are not up to date. Okay, so then you can calculate, yeah, and then it calculates again, and now it's up to date. And the results really don't change that much because the depth, is quite close to the end of tubing, so we shouldn't expect here really any big change in the bottom hole pressure. If it has been shallower, maybe it will be a kind of a bigger difference, okay, compared to the previous case. Now let's again click edit. We're getting very used to this to edit the well configuration, the well completion. And now again, I go into the valves here, but now I want to add more valves. And when I add more valves, automatically, because it's not assuming that it will inject how much through each or how much do you want to inject through each, it will say, give me the opening and closing pressures, and then I will find out through which valve you are going to be injecting, okay, depending on the pressure you have and the pressure that you need to be in the range. So it will find out which one is which one is open. And we go back to the PowerPoint to show you where that is, to the PowerPoint slideshow. Okay, you see here on this slide, okay, we have three different. One is very shallow, it's like half of the tubing depth. 3,000 opens at 1,000 psi and 900 psi. Then the other one opens at is at 5,000, opens at 854, closes at 834, and then 7,000. So that will be like closer to the end of the tube. So let's add those, and then we can see something interesting. Okay, so 3,000. And here, be aware, something we number the valves from bottom up. Okay, so this number that it has there, it tells you one is like closer to the bottom of the tubing, and as it increases, it goes to the top. Okay, just don't be confused. 5,000, and then I add one more. Okay, that will be 3,000. Okay, the opening pressure, closing pressure, opening 854, and then 782, 942, 834, and 762. Yes, I think that's correct. I'll give you some few seconds to. Okay, and I think maybe Mo, you can correct me here if I'm wrong or not, but this option is in case from the pressure calculations you find that actually no valve, maybe you need a very high pressure to be able to inject through that valve. Then it's assuming that the last valve is always open. So it will assume that whatever you're injecting, it's going to go through the last valve. If through after that analysis, looking at which valve should be open, you find none, then you go through the last valve.
Yep, that's correct. And then in many cases in your valve tally, like in your Excel sheet, where you have the valve details, you'll see that the last valve is an orifice. It's not really a valve; it's just an orifice. So you know that valve is always open. So it's not just an artifact of a calculation. It's actually many times it's the case that you have it installed as an orifice and not just as a valve.
Yes, and then I click, let's say, check again, 3, join 3 valves, and then I save, and then I run now the again tells me that the indicator that there is something that has changed, and I should be rerun again. Okay, and now again the results are there, and actually it also doesn't change that much. But something that is interesting to see, to visualize, is which valve are we injecting through. Okay, what has the software found out that, which valve is going to be open. And then here at the top, you see we have the BHP plot that's showing the pressures, but then you have the gas lift plot. And then you can go in there, and I don't know if you can see there, you can isolate the gas lift valve depth, but this point, which is like a gray or hollow, a round point, okay, you see there that which one is active when. Okay, so nothing is active here because you don't have any, the gas lift rate here is 0. But when you start injecting gas lift here, actually the shallower is the one that is open. Okay, you see this at 3,000. And then at some later point in time here, remember that from the data, we got some very small gas lift rates. And then at some point when I increase, they go a bit lower at 5,000. And then here you see the depth, okay, goes from high to low, from low to high. And then here actually stays at 5,000. So at the end, according to the software, I'm only using the lowest at, according to these results, I'm only using the lowest for this period. Okay, I'm not using I'm using the one at 5,000. Yep, here you see, yep, other things that are shown here is again the tubing and the casing head pressure and the bottom hole pressure, the one that is selected, okay, which in this case will be the gauge pressure. That okay. Then we go to the last option, which is automatic. That means that you don't have, let's go back to the screen where we have the well data, and then we have the completion configuration information. And here again, we go to, we can change to automatic. And in automatic, it will automatically find by doing, checking the pressure in the tubing and the pressure in the annulus. So where the two meet, where the two become the same, and that will be the place where you should have injection. Okay, if we go, I think we have a nice slide on that. Okay, let me see. Okay, it's doing that calculation. You have the two pressures are known, tubing head pressure and casing head pressure. Then you can run a calculation, and then when those two meet, essentially they cross, that will be the injection depth. Okay, and if you have you don't have any information about the valves, that should be kind of close to where you have your injection point. Okay, let me go back to the software. Then okay, then we change it here to automatic. Then I save, and again we'll give you the message something is not up to date, and then I click calculate. Okay, and now let's inspect. You see the results. I cannot really see any noticeable change. Actually, they look quite similar. But let's look at this gas lift plot. And here you see the depth that is calculated by the software using this automatic option. As you see here, it has a few points in which I have 3,000. Okay, a bit shallower, but around 3,000. So that kind of is consistent with what we found before, that the shallowest valve was open first. And then when you increase, when you go later in time, you see that actually the depth goes down all the way to 5,000. Here it remains kind of quite consistent at 5,000. So that's also similar to what we found when we were using the actual gas lift configuration, the valve configuration. Okay, that later it starts injecting deeper, but at no point you're injecting at closer to the end of the tubing. At no point in time. Okay, let me go back to the PowerPoint to see where we are. Okay, now let's calculate the pressure. Now using the quiet silent side. Remember, so far we are So we are first finding which valve is open. If we give different valves, we give which valve is open. So from that point and downstream, I have to consider the rates of reservoir, oil, gas, and water, and gas lift rate. Okay, so I start with that pressure, calculate the pressure up to that point, considering all the rates. And then from that point and below, I have to use reservoir rates only, because that's the point at where the gas is coming in. So here I might have tubing flow, then I reach the end of the tubing, and then I have production casing flow, and then I reach the top of the formation. And that will be my bottom hole pressure. But I can also estimate that pressure through the quiet side. Okay, that means that I have that casing head pressure that's also reported. We also know that we have it in our data. Okay, I don't know if we have it here. Well, no, it's a bit too many slides before. But I have that casing head pressure. I have the rate of gas lift. I can calculate all the way down to the valve, to which valve I'm injecting, okay, through the annulus. And then from there I have that pressure, and I can just proceed. Let's say flow through the tubing as before, flow through the tubing, the rest of the tubing, using the reservoir rates, and then flow through the production casing through using the reservoir rates. And this should be actually similar to the one before. The only thing is that we have a small pressure drop across the valve, because it has to go through a small passage, and then you have some losses, localized losses. So then might be the pressure, the assumption that the pressures are exactly the same is not 100% correct, but it's it's a kind of practical kind of an engineering assumption. Okay, so let's look at the interface here. You see that let's go back to the interface again. Click on well data and completion information. Here it's saying use the flowing side, so that means it's going to follow like all the production fluids where they're going from. Okay, but then you also have a quiet side. In this case, the quiet side, what is referred to as the quiet side, is where the production fluids are not, which is the annulus. Okay, and here it's where do you want to compute the static down to? Here the more correct will be to say down to the gas lift valve, okay, because that's go back to the PowerPoint to see if I can clarify this. If I say at the end of the, let's say I'm injecting at a shallower valve here. Okay, so I calculate the pressure there. Okay, then I assume that pressure and the pressure inside the tubing are the same, and then I proceed down through the tubing and there. But if I'm, let's say if I select their end of tubing, I will be doing the calculation all the way down to here, and then assuming that that pressure is equal to the tubing pressure or to this pressure, and then using the reservoir fluids. And that's only correct if I'm injecting at the end of tubing, if I'm using a pour buoy configuration. Okay, so I should use that option. I should use, if I want to use the static side, I always should use the gas lift valve. Okay, that's the one that is more consistent. Okay, then I click save. And now let's compute to see what do we have. Again, tells you there is a warning, something has changed. Okay, let me go to the BHP plot. And I obtain the following. Yeah, I have the gauge pressure and I have all the different correlations. Okay, here looks quite similar to what we had before, but here what happened here at the beginning. For this period, we had 0. Maybe I can highlight it here. We can go to the production data. Okay, for that period, if we look at the gas lift rate, which is this the dark discontinuous line, you see that I start to have some gas lift rate just at this time. Okay, for all the period before, I had no gas lift injection. So it might be that actually I had there simply a packer, or I had something that simply they were not connected, the annulus with the top of the formation. Okay, and similar thing, a similar thing here. Okay. Okay, where I have periods where I have no gas lift injection, it might be that the estimation is not correct, because might be something the well might have had a different configuration. That's just speculation. I think this is data, real data, but we don't have the actual completion history of the well. We don't have actually all the completion changes that have been made, so we cannot verify that. But looking at just the gas lift rate, that's kind of a indication of what could have happened in this well. Yes. Maybe we can take. Let's go back and change it. I want to take. I think it's a bit early for a break. We take a break a bit later, but I want to show the smoothing functionality. Okay, these pressures at the end are going to be used later for something, right? For reservoir, for production studies, and they are quite spiky. So I might want to smooth them out just to get rid of these bumps. Okay, so let's go back now. Let's don't do calculations on the quiet side. Let's do calculations on the flowing side. Okay, and then recompute using the automatic valve location. Yeah, and here it's not so spiky actually. It's actually quite smooth, but I want to show you how to do it. So you click here. If you see here, the legend tells you this is the bottom hole pressure that will be used in all the calculations that require bottom hole pressure values for that well. Okay, and here you see that you're trusting completely on the correlations. Here you're using the gauge value, but I can also click here on custom PWF, and this is the data. Here in this case is the measured. Okay, but I can say, for example, I want to use the Vexenbryo, which has some spikes, and I want to like do a smooth the curve. Okay, I want to get rid of these maybe these bumps, which might be a bit artificial. Okay, then I click auto fit. And here is using 20 samples, so every 20 points is using 20 points to create this average. Okay, if you think that that's too simplified, you can actually change it to maybe 10. Okay, and then click auto fit again. Okay, and then you get like a much smoother trend. And these numbers, these are the ones that are going to be used in your other analysis that you use in the software. Okay, I think that also if you have like let's go back to the measure, for example. You see here that this might be an outlier. Okay, let's say you use a sampling frequency of 1, so you're going to use all of them. Okay, but let's say you don't want to consider that point because you have a kind of a big spike. You suspect it's something with the sensor, with the electronics, with the cable, whatever. Okay, that you don't trust that measure. So with that, you can use this tool here, quite useful. All of these tools, I myself, I don't use, I don't have learned yet to use all of them, but this one is quite useful. Remove point. Okay, and then I say this point, I have to select it. Okay, and now it will be excluded from the output from the smooth output that you're going to be using. Okay. Okay, I have to lasso means that I have to kind of round it, circle it. Okay, and then it's going to exclude those 2 points for which I visually suspect there was something wrong happening there. So I can also pick the point and move it up, and that I do with let me see. I have to first
just hover over the point.
Yeah, but I have to remove the lasso first, right?
Yeah, that's fine.
Yeah, still the lasso is selected. So how do I unselect it?
Just click on the lasso remove point there, and then click on that first one.
Mm-hmm. Okay. Yeah. I tried that before, but okay. So you can actually change those points if you to make the trend a bit smoother. You can change points individually if you want by dragging them up or down. That's useful, for example, for the other case in which we have like a valley. Suddenly everything dropped, so we can actually either exclude those points, or if we still want to keep the points but don't include the valley, we can actually drag them up and down. Okay, and that will be the actual profile that will be used. Okay. I think we can go a bit more. We had a break at almost an hour, like 50 minutes ago. So I think we can. I suggest we continue 10 more minutes, and then then we take the rest. Let's go now to one thing also that we have to that also functionality in the software. We are going to see it later, but here you see there are some buttons at the top, and these are different things. So one is water. This critical rate depth, that's for liquid loading. We will see later what it means. That's for the water and lift gas. So for example, if your lift gas it has let's say comes from a different field or you're buying it from a different source, so it's not the same that you're producing, so you can actually specify here the specific gravity. So that might be more accurate if for some reason you're using gas from, for example, from the system, not from your well. Okay. And here you have the calculation option. And here is saying that you compute even when gas lift rate is 0. Okay, and for some cases might be that you don't have that there was gas lift, but actually there was no data reported. There is no data recorded. So if you compute any bottom hole pressure, that will be wrong. So then in that case, you have to untick that option, and it will not compute bottom hole pressure. We can do it here. It will not compute bottom hole pressure for that date. Okay, you see every point in which the gas lift rate is 0 simply doesn't compute any bottom hole pressure, because you are sure that was gas lift. Gas lift was running continuously on that well all the time, but simply you have some points in which you have no data for some reason, and you don't want really to calculate the value which is untrue. That is not correct. Okay, so in that case, the healthiest thing is to use that option. Remember where to find it here in the well and in the calculation options. Okay, this option. But if you are okay with calculating, you're fine with neglecting gas lift rate. It's correct. You're sure that what was measured, you trust it completely. So then you use that option, and then it's going to calculate. Okay, and then if you have gauge values, okay, here's something interesting, is that this custom BHP that we made here, filtered, now it appears with this yellow color. Okay. Okay, and since we were using the gauge pressure values, so that's it's going to be most similar to that one. But except for these changes we made here, you see that we moved these points a bit up and down, and we removed this outlier here. Okay, this value we removed. Okay, but if you have the gauge value, then you can decide if having that option on or off, it's a good alternative or not. Okay, if you're unsure if the values were measured or they're actually 0 or what it is. Yep. Now we reach the rod pump, but I think here now I will suggest we take again another 5-minute break. So until we are now 02, so we continue. For you, it will be what, 11:02, right? So we continue until 11:07, and then we take the rest, which is not much, I think. Okay. I see that there is a lot of action in the chat. Luckily, I don't have to answer live. Otherwise, I will become a bit crazy. But I think you're getting good answers there. I will try to pitch in if I see that something needs my discussion. Okay. See you in 5 minutes. Okay, now we're back. So now the next example we have here is a rod pump. I think there were a lot of questions in the chat, but most of them have gotten an answer. Let me see. There was one more thing. Yeah, it was on there was a question on the plunger lift. In plunger lift, if I think here in the wiki, I hope it's a good explanation of how it kind of the fundamentals, the basics, how it works. But essentially, due to the cyclic nature of production, your bottom hole pressure will be changing during the cycle. It's going to be changing when it's charging, it's going up and down. So here you see your wellhead pressure, for example, and the rate, you see the change in the rate from the reservoir. This is the red, okay? And because of that, your bottom hole pressure will also be changing. What we try to do is try to estimate an average. So we say how much was produced in average during the stage, and then calculate like an average flowing bottom hole pressure to produce that. But if you really wanted to calculate that bottom hole pressure properly, you have to do a dynamic simulation with that step of maybe seconds, of maybe hours. So depends really for what you want to use the data for. But if you want to use it for any reservoir, how do you call it, workflow, then having something so detailed is usually pointless. That you don't want to have something in the range of seconds. That usually is more for diagnostic. If you have a plunger lift which is working properly, you have to tune your plunger lift. But usually, if having a bottom hole pressure detail to the range of seconds or minutes, that is what you will need here to model that behavior. It's a bit overkill for kind of reservoir workflows. Okay, so that's why that's the assumption it's made. It's you take calculate the effective rate. For that, you have to calculate how the total, and then only consider the cycles that you have, or the number of cycles you have in the day. Or if you have, you can also take the fluid level, and usually also that value is averaged. That value will change during the cycle, but that value is averaged throughout the day. So you will get an average liquid value and then liquid level number. And then from there you calculate to the bottom, you calculate to the top of the formation. So I think all depends on what you want it for. But if it's something for that diagnostic of plunger lift, this is not the tool to go for. But if you want to get a bottom hole pressure representative to use it later for something else, then this is the way to go. Let me see. Okay, rod pump. Okay, so now we are going to say goodbye to this well. Gas lift, I think I covered most of what I was supposed to cover. Mo will, tell me later if I didn't, but I think that was most of it. Then let's go to rod pump. You see here I have my wells: gas lift, ESP, correlation rod pump well. Again, here we have to already, there is a lot of pre-populated information. We just have to add the pump itself. Okay, we can look at the production data. Okay, you have again oil, gas, and water. Here in the table, you should have the liquid level. It's some point here. Okay, here start to have a liquid level. Remember, in a rod pump, we are using the liquid level, and assuming there is no bottom packer, there is communication throughout the annulus all the way down to the formation to calculate the pressure. And here we have the liquid level value that we need to make our calculations. Okay, so we go back to bottom hole pressure. And it's not shown here. Here we have a gauge pressure, and we have a casing pressure and a tubing pressure, which is, I think it's this one here. Okay. I think here it becomes 0. So why let me see if on the slides it is shown. I think we had one nice. Okay. The thing with a rod pump, it's a special type of pump which we call a positive displacement pump. So that pump acts in the fact because you have two valves that they are kind of controlling. You have a volume. It's like, imagine, in a way, it's not like that, but it's, if you can imagine like a piston, like a syringe, that you're pressing the syringe. What will come out of the syringe, the rates only depend on how fast you push the syringe. Okay, it doesn't depend at all on the pressure you have at the outlet of the syringe. So if you're trying to inject that into, let's say, a person, or you're trying to inject that into a stone, or you're trying to inject that into the air, really it doesn't, the how much you inject, it really doesn't depend on any pressure. It only depends on how fast you're pushing that syringe in. Okay. Considering that you have enough power, okay, considering that you have enough force. Of course, injecting in a rock, it will be much more difficult than injecting a human being or injecting in the air. But you know, that's the whole principle. So really, how fast I move this up and down, that's what is affecting your rate. Okay, not so much the pressure you have across. You might have a big pressure across that you have to lift, but it should be able, in principle, to push it up if you have enough power, if you have your pump motor is big enough. So that's why we don't do calculations across the pump, because really you have those valves there. It's like a piston that disconnects the suction from the discharge. Okay, so you, and there are some, might be some ways that you can try to do an estimation using some performance curves, but usually this pump is so special because it disconnects in outlet suction from discharge in that manner. Okay, so think of it like a syringe. Doesn't matter, I just move the finger fast, and that's what's defining the rate. Yeah, so that's why the more best method that Whitson found to estimate the bottom hole flowing pressure is to use the liquid level. Okay, so then I have to make first, I might have some flow of gas through the annulus. So then I flow from casing head pressure. I assume take that flow, consider no liquids coming with it. Then I reach the liquid level that I measured with maybe some automatic gun. And then from there, I calculate down to the end of, where the pump is located, usually the end of the tubing. And there the column might be, here you have in the manual some other nice figures. Above the plunger lift, you know, if you have gas flow, if you have no gas flow, so it might be simply a liquid column, might be whatever fluid you're producing. But usually you get segregation, you get like oil, and then you might get some water, but segregation of phases. And then if you're producing gas, depending on the amount of gas, you might have a situation in which you have a column which is very gassy, or you have a column which is less gassy. So that is calculated. You calculate an effective density of that column, and then you calculate the pressure at the suction of the pump, and then from there you continue down to the pressure, to the pressure, bottom hole pressure. Okay. There are some details there in the wiki to see how we do that calculation. Some things are based on the data from other people that have worked with that. Essentially, it's a stagnant column of liquid that you have gas flowing through it, and it's a bit special. It needs a bit of a special treatment. Okay, so now let's input that that data. Okay, you see here is something special. We are not going to assume there is rod pump from the beginning, but we will be applying rod pump from a given date. Okay, from the 5th of March of 2015. That's where some some workover was made on the well, and then you made you change it to convert it to rod pump, and that's where this one will be applied from. Okay, so we're going to use that data. I think all of that data is there. There's the natural flow, but we're going to input the rod pump data. Okay. So again, be careful to select the proper well, rod pump well here. Okay, and then I click on this edit well data. This we are not going to change. This will be the same. Okay, this we keep it as it is. We don't have to input it anymore. Okay, this is the original configuration. Was just actually casing, just no tubing. Was just flowing through the casing. This well. Okay, 4-inch casing, and then here I click this plus, and then I will add a configuration that will appear here now on the tree on the left. Okay, so now you know that that well has experienced at least 2 changes during its lifetime, and here we put the date, and the date we can actually input just like that. So it was the 3rd of So 5th of March of 2015. Okay, or I can pick the date if I want. Okay, let me get now the okay. Here we have a casing, bottom MD that will remain the same. I still have this 4-inch production casing, but now I have tubing, and that tubing will go down to 7022. And this is 2441. Maybe we can pick it from here to this 722, 2441, 2.872 and 78 K tubing. Okay, and here the flow path will be tubing. And you see when I activate tubing now, it allows me to select an artificial lift method. Okay, so the artificial lift method will be rod pump. Okay, and here so it's going to follow that that procedure. Okay, let me check again the numbers to make sure they're not making any mistake here. 22. Yep. Okay, tubing, rod pump, and that's it. Okay, save. And from the date, be careful. You have to be careful where it applies. And here, something useful I found useful is this Wellbore configuration dates. Okay, so it tells you here that there was a change. This vertical line tells you there was a change in the configuration. Okay, exactly in this 5th of March. So that you are aware when you plot the bottom hole pressure that you're using a different path, different you can be using a different configuration when you calculate on the left or on the right. Okay. Then I run. Okay. And that's what I found. This is the gauge. So actually all of them are quite close. And here this began to deviate, but still Bex and Brill apparently it gives a kind of a good similar value. And here also the gauge are quite close to the prediction. But here you have something strange. This was your gauge. And here all of them are kind of, first they are overlapping and they are going to a very high value. Okay, so what could be happening here? And you can cheat because you have already the printout of the slides, so you can kind of okay, what happens here essentially is that at those points I don't have a liquid level. Okay, I think the liquid level is so 0. The value for some reason was defaulted to 0, and then is making like if I have a very big column of liquid. Okay, the liquid is going all the way from the top. Okay, if I look at my slide. Okay, this liquid level is not 5,000, is not 5,500 like we saw before, but it's actually some value up there. And because of that, then the pressure there will be much, much higher at the bottom. Okay. So how to fix it? Here is where it becomes useful to use this custom bottom hole pressure. Okay, this is the measure I want to use, for example, the Bex and Brill. You see you have those 2 points there. If I want to keep all of them look fine, I don't want to do any averaging, but I just want to remove those 2 points. I put the sampling frequency. Okay, you see you have these 2 points that for those dates, maybe there were no liquid levels or were 0, were set to 0. So actually I can move those down there. Okay. And now this will be out. Okay, I can also use this lasso outlier tool to bring it down. Another way I can fix it is again here you remember these calculation options we had for gas lift, and here we're saying allow it to compute when liquid level is 0. So I can simply say, well, don't. Can I rerun? Okay, and now should maybe I didn't select it. Compute. So now it shouldn't compute it when liquid level is 0, but it's still showing something. Maybe it's not. Is it run? Yeah, I think it shouldn't. Let me check with the master here, Mo. If
Yeah, let me check her.
I mean, just one thing that sometimes happens is that you need to refresh your browser. So for that, you use either this button or Control R. And because it's a cloud software, so it needs to fetch values from the server. Sometimes it doesn't reflect the change. But here is, I don't think it's maybe something else. Maybe I found the bug live, so that could be that's actually a very good thing to find a bug in the software that we need to fix. So, but I don't think so. I think this has been debugged many times before. Okay, we continue. I think you can also change the input to the calculation. Okay, you can change here the input to the calculation here. If there is some data that you think that it should be excluded, you can also do it from here. I went back to the production data screen and I click here smooth. And here you have all the some of the time series, that oil, gas, and water rate. And I can decide to smooth them. For example, not use them straight like they are. Let's see, for example, the oil rate. Okay, here I use maybe too much. Let's use 10. Okay, maybe a bit too much. Let's use maybe 5. Okay, and I will be much less noisy, and then that might give you like a more smooth bottom hole pressure. Okay, but what we are concerned here is the liquid level. So we select here the liquid level. Okay, and but I don't see here the ones that are 0. Okay, maybe they are just too close to each other. Okay, but I could use this also to exclude those points if I have a point that doesn't make sense.
Yeah, I was looking at that. I don't think the liquid level is 0 in any point there. So it might be that you see it.
And this Oh, yeah, okay. So this is
That's
maybe
because of the
something else.
gas, I
Maybe the
think.
gas rate. Okay. Okay.
Yeah, that's correct.
Okay, so was not this my speculation? Okay, it was yeah. So we saw from here that it's not actually we have liquid level, which is see here 5,500 constant for all that period. Okay, what we have is if we look at the gas rate, that's you're right. Okay, it goes down to 0 at some place. Where are we? That was when. Maybe we can take a look back here. Okay, this was close to March 22. Okay, so let's look at there. See what do we have. What's rate and dates? No, but the gas rate is not 0. It's
if you zoom in there, I think there you'll see it. Just zoom a little bit between March 22 and March 8. Just click on the plot to zoom directly. Yep. There, and so you see.
maybe I have to go a bit like this. I see that we have points for.
Yeah, so it's March 18 and March 19. That's you're missing. Okay, looks good actually. me see here real quick.
It's also important that we put not only you to work, but also us ourselves. We have to work a bit during the course. So sorry, putting Mo on the spot, but now that you know that we are, doing it in real, we are not, we are not bluffing you with animation and.
I'm
and
checking
PowerPoint.
actually here, and in the well, it doesn't seem like there is. Let me see. So we can just. Doesn't seem like there is a gas rate there, but I'll double check that, Milan, and then you can.
Okay. Yeah, we continue and then we can go
forward.
back to that issue. Okay? Not to, not to create too much stress to try to solve it live. That's, I don't think that's very healthy.
Yeah.
Okay, but essentially here we have an issue, and I thought was a liquid level, is not. I thought Mo thought was the gas values, is not. But essentially, if you don't trust, I wouldn't trust that number. So you can actually in the output, you can simply, you're getting something like that. You can remove those points from there. Okay, and then you won't use those points. I think that was the main issue. And then you have to do some more detective work to find out why are you getting this there. Maybe some of you, we can make it a contest, and then some of you can win a prize if.
Yeah, I think there's just if you go to the production data there in Milan, just quickly, there's is what I found is there is a bug, I think, when you click on the smoothing with dates, and that's why you were not seeing it correctly. If you do the smoothing with time, you should probably see it. If you just keep it in time, I think there should be zeros in between time step 77,
here.
76 and 79. If you try to zoom in between those.
These two? Okay.
Yeah, there you go. Yeah.
Okay, so it's
it's like 77 and 78 that are missing there, and those are the gas rates that are missing. So if you just use the plus button there that you have, now that you're zoomed in, and then you just basically connect those two with linear interpolation or whatever, just put a point there. Oh no, just click one, and then click another one here, and that just fills the gap there between those at least. And then you save there. And then
now we are changing the input, not the output. So yeah, be aware of that. Now we are changing. We input some production data, but we are saying something is wrong with it, and then we are now rerunning the calculation with that input data. So that's very different from modifying the output. Okay.
Yes. So that should.
Not really.
Didn't work. Okay.
Maybe it's using. I didn't apply. No, I didn't apply it demo. So that's the gas rate, and it's between these two.
77 and 78, I think. So just zoom around that box. Just zoom, I think is better.
And then here I have to say gas rate, use that, and then save. I think that's how it is.
Yeah, you can see there the GOR changed in your plot now. Yeah.
Okay, now it went back to okay. So we found the reason is not the liquid level. It's it was the gas rate, like Mo said, but was actually a bug in. Okay, now we go to the well with the electric submersible pump. Remember to select here the proper well. And if we go to the theory here, that we need to have actually this pressure value at the that we call a gauge pressure at the suction of the pump. We need to have that value available, okay? Because in that actually in a ESP there is a performance curve actually that connects the output and the suction and the discharge. So we could have used that curve if we have it to kind of calculate if you have the discharge to calculate the suction. It's not like a rod pump where they are disconnected. But in this case, that functionality is not yet available in the software. Maybe it will be in the future, but it's not available. Okay, so what we do is that usually the ESP has it prints out that value of the suction pressure, and then we are simply doing a calculation from the gauge that will be suction pump pressure all the way down to top of formation. Okay, so let's try that. Okay, and you see when you select, we will see now from the interface, when you select the electric submersible pump, automatically this gets turned on because you're going to use that gauge pressure to sand phase, and you have to provide the gauge depth. So for the gauge pressure you provided in the input data, what depth, at what depth is the suction of the pump. Again, it should be the suction. Sometimes the pump is like a string, which can be quite a few 100 feet, but it has to be where the suction is located or where the sensor is located. Let's see here. We go make sure that the SP well is selected. Then we enter here into the edit the well data. We are here in the completion. All the rest we leave as it is, tubing, casing, etc. But now we select ESP, producing through the tubing. And here we have to be very careful to input the gauge. Otherwise, it will assume it's at 0, and it will assume like the pump is at it's essentially at the top of the well, which is not correct. Okay. So if we go to the production data, back to the production data, here we have gauge pressure. That is actually the pump suction pressure. That's what's going to use to go down to the top of formate to bottom hole. Okay, here we calculate, I think. Let me make sure that the data is correct here. Yep. Then we run. Okay, so see here the gauge, and then you see your bottom hole pressure, and here all of these correlations, they overlap essentially. You see here this overlaps with that one. Maybe there is just a single phase flow. That will be my guess here. Okay, and you see that actually the gauge, the bottom hole pressure is higher than the gauge, and that is because you have okay, because it's the pressure to flow from bottom up, you have to have a higher pressure here than there, and that's why the pressure should be higher. Okay, we are using the gauge. That's our suction pressure. So that's the delta P is the pressure drop you have from top perforation, from top of formation to pump suction. Again, it remains, according to this one, relatively constant with time. Yep. Now, was a question about liquid loading. That's the next example we have here in our slide deck, which is what happens if we have liquid loading. And for that, we are going to go back to or if we want to check for liquid loading, how we are in terms of liquid loading. Let's see here, and I select the liquid loading. Gas is dry gas well. Yeah, and I can, here I don't have to do anything. I just have to run it as it is. Let's look at the deviation survey and then the well data. It's simply flowing through a casing, which has almost 5 inch. And yeah, and is flowing through the casing. Okay, there are no more options there. And then I run. And here automatically it calculated, apart from the values of bottom hole pressure, it also calculated the liquid loading values. Okay, and if you go here to liquid loading plot, it's going to show you what it found. Okay, so that's the total gas rate, and here we're using Turner, the correlation of Turner, and it's telling you that I need to have at least, for every point in time with the conditions given, I need to have at least this much rate or higher to avoid liquid loading. Just to refresh your memory, liquid loading is when you have, the gas rate is not high enough, and you have some liquids always produced with the gas, that the liquid starts to, simply starts to occupy a lot of the cross section of the pipe. The holdup of the liquid starts to increase, and at some point actually starts to travel downwards. Okay, the gas is not enough to carry that liquid up, and it starts like a slushing phenomena that, slushing up and down. It's like the well is choking essentially. And and that's liquid loading. And we have some criteria here. You're using Turner. You have some criteria to calculate which rate you need to avoid that to happen. Okay, so here it tells you that during the first period of production, everything was nice and healthy. But then here at some point you went below, maybe something temporarily, but then it went up again. Then it went down and up, and then suddenly you're getting closer and closer to that line. And you see your gas rate behavior is becoming more erratic. It's not smooth, declining smooth like it's doing here, but it's going more and more erratic. And that's due to liquid loading. That is a sign that you're maybe entering into the liquid loading and things are deteriorating quite quickly, and that is affecting the performance of your well. Here, this rate, you can essentially, you have to go into all the depth that you have in your well, and you have to find for which is the most critical. In Whitson Plus, there are many locations that are calculated by default. So wellhead, gas injection, top perforation, end of tubing, or specified. You can even specify a depth where you want to calculate this rate. In this case, it's just end of tubing. And there usually you pick the point where you have the highest pressure, because there the gas rate is usually smallest, or the gas velocities, no gas rates, sorry, the gas velocities are usually smallest. So that's where it will be more critical if you have a lot of liquids, that the gas won't be able to carry that liquid up. But it's also true that when pressure goes down, then you get more liquids flowing, coming out of dropping. Might be, if it's a gas condensate well, you might have some more, liquids dropping out. But usually you check at where you have either the biggest diameter and where you have the highest pressure, and that's usually close to the bottom hole. Okay, in this case here is end of tubing. But it's calculated. If you pick another one, wellhead for example, it should show you. Yeah, now it changed. You see, now I have to calculate. Okay, didn't change that much, I think. It shows you like changing depending on the location where it is. And you can also have other criteria. There are other criteria that are used. Coleman was here you see how it's changing. It was a modification to Turner, and you have two other that were Belfroid, for example, modification with inclination. In this case, I think the well is relatively vertical, so I don't think that will have any effect. Okay, this part is maybe not changing that much, so it doesn't have that big of an effect. And then there is another one that is using a slightly different approach, Nagu, and this is quite conservative. That actually tells you that you're always loaded almost at a very high rate. So you have to also always have with the data. I think here kind of what this Turner is saying makes sense, that you are maybe something a bit higher, but Turner is ballpark kind of accurate. Yep, so that was the liquid loading plot. You can use it to see every point in time where you are, and using different criteria and using different locations. If you have a special location which you think could be critical due to the size of the inner diameter or the pressure, so you can also do it here. Now let's go to the last example, which is BHP correlation tuning. Okay, and in this case, we are lucky enough that we have a gauge, and that gauge, we want to tune the correlation. We want to predict it exactly. We want to, we're not happy with having a spread around that, but we are, let's say we want to match it exactly, which I warn you is not always, we should allow for some variability, for some uncertainty. But if you want to do it, then you can do it. It's also common practice. Okay, so here we calculate bottom hole pressures. Okay, you select the right well, BHP correlation tuning, and then click here the button. And then you see we have a difference. And it's kind of, what is strange is that it's constant. Okay, here at least it looks constant, and here it starts to deviate, and here you start to have more spread between the correlations. And so my guess is here, since all of them overlap, you might have single phase flow. So here you have no gas, simply you have flow of oil and water, or simply oil. Okay, but here you start to have some gas coming out of solution, and then you have some differences between the correlations. But still you have here in that region, you have a difference between, you know, the single phase calculated and the single phase measured. Okay, which in this case the gauge, I think we can check here where the gauge is, but the top perforation is 7828, and the yeah, it's not there, but the gauge is exactly at the same place. Okay, we should maybe add the gauge depth there. Actually, it's not exactly there, but it's a bit, yeah, top perforation 78, and what I have here is 7595. Okay, so the gauge is not exactly at the bottom hole, but it's a bit shallower. It's a bit higher. Okay, that shouldn't matter. The tuning is made, if you give the location of the gauge, the tuning is made calculating the pressure at that location. Okay, with the correlation. It's not using the bottom hole pressure, but it's using the location at which the gauge is. Okay, so it's here is end of tubing. Okay, and it's using gas lift, and it has some valves, so it's not just producing naturally, but it's using gas lift. Here you can see just one valve at the end of tubing. Okay, if I rerun here, nothing should change, because it shows you, yeah, the gauge and the bottom hole pressure that were calculated. Okay, so first we're going to do two things. So we're going to try to, here is single phase flow. So here we know that there is no effect on correlation, simply it's effect that maybe the fluids that we are using, they are not, you know, they're not, it's density and viscosity, what we are, could be different there. And so one thing we can change, since there is water being produced on that well. Okay, this is the water. Okay, the water that we are using, the salinity affects the density a little bit, especially if it's very high. Okay, let me see here if I go on the slides. Yep, this is a single phase. Before doing the tuning on the multi-phase, before showing you that I'm annoyed by this section in which I know there is no multi-phase flow, simply single phase. And I know that the properties affecting that pressure drop is density and viscosity. And the oil and the gas should be correct. So I'm suspecting something to do with the water. Okay, PVT it's correct, and then the water is what is my main suspicion. Okay. And if you see here, there is where we can change the water properties. I think I went briefly through it. I don't know if you remember, but here in the bottom hole pressure, in the well data, here I have the water properties. And here you see that's the density at 0 ppm. But if I increase this to, let's say, 100,000 ppm, it's, sorry, went away. Okay, it's changed to 66. So it changed a little bit. It changed around, how much is that? Less than 5%. Okay, and that can affect actually my values there. Okay, so what I propose, just to match that part, is to change that salinity. Well, you know, we're getting formation water, might be quite salty. And here we have, for reference, some values. We have, for example, seawater is 35,000, and any brine that we are using goes to, you know, from that value to the saturation. So whenever if I add any more salt, it's going simply to deposit. It won't, the solubility limit, and that's around this number, or 300,000. So let's pick a number. I think I found that for this case, a value of 150 gives a better match. Okay, then I save and rerun again. Here I didn't change any completion configuration. I simply changed, and now you see the match is actually quite good initially, but then I still have a deviation. Okay, so it might be, yeah, might be something else. Okay, but the main point here is just be careful with your water. Be careful what kind of water you're using. And if your water in any has a significantly high content of salt, something that changes the density significantly, make sure to use the proper number. And if you have data, in this case, we are lucky we have some single phase data, then that helps you to find out if maybe your water properties are not set correctly. That water rate salinity might change with time. Initially, when you frack, you get some water that has a different salt content than what you will get later. But that's unfortunately not possible yet to do it in the software. Okay? But maybe in the future, the salt content changing with time. But now let's go to the fun part, which is to try to match this multi-phase flow, the correlation. Okay, but be aware that here, even in the single phase region, we have some spreads, so that will affect my match later. So for doing the fitting, I go up here, you see you have a button called tuning. And here I can tune any of the correlations to give a better match. And it's changing the, in the delta P pressure gradient expression is changing, is adding a multiplier to the friction and the hydrostatic term, the gravity term. And then it's trying to change them until these values get closer to the line. Okay, and that's done not at bottom hole, but that's done at the gauge depth, at whatever depth you have a pressure measurement. Okay, so I click tune. Okay, be careful. It's a very sensitive operation, and then you show fit. Okay, and now you see actually that here you have still the deviation. This is single phase flow. We didn't expect it any better, but here the match is better. Now we can tune all of them and then see how it turned out. So sometimes the factor magnitude tells you how much you have to modify the original correlation to match it. And the friction, like I told you, usually the effect is less, is 30%, 20%, 50% of the total pressure drop. So that doesn't affect much. But this one is the one that has the biggest effect. And now you see that the fit was such that all the correlations, they give the same similar result. They overlap, and they are much closer to the gauge data. That is at gauge depth. You see here, it tells you very clearly that's at gauge depth. That's not bottom hole. If you're happy with that tuning, you want to use it, you trust it, you have verified that it works for other for, let's say, into the future, you trust that it can be forecasted safely, you save. It's going to save that tuning parameters and then calculate again. Okay, and now you get like a very, very good match there. Okay, but not here because that's a single phase region. Pumps, again, if we're having a ESP pump and we have a pressure measurement, the pressure is measured at the suction, not at the discharge. If we wanted to make that tuning, we need to have two pressure points, a wellhead or tubing, and then we need to have one at the discharge of the pump. We cannot have it, we are not modeling the pump, so it's worthless, really. We cannot use it at the pump suction. So don't do this for ESP. It's only for every other case. And this last part is so here I have used a lot the interface for, if I want to do more like an engineering, or I want to do like a graphical to be inspecting everything graphically. But if I do things, I try to make them more automated. I can use this mass upload feature. And in mass upload, I can first I have to make sure that the data is in a format that it will be read by the software. In this case, this is their own Whitson template. I think we have an example on the slides. Okay, it looks something like that. You have the name of the well, you have the date in this format. So it's a date separated by dash and then the time, and then you have the rates in these units, and then you have all the other things. Okay, and then you have, this is the data for, this is another tab in which I have the data for the completion. Okay, so here you see the flow path is tubing, the temperature, tubing bottom MD. So everything that we have set graphically, you can set it in a file, and then that file you can upload it to the software. Just drag it here. Okay, after you have the file, it can be for multiple wells, can be for one well, and then and here you see ignore or merge or overwrite. If you have already a well existing that you want to overwrite, yes, and then for this part, I think maybe Mo, if you have any comments, I know that a lot of people use the API connection, so they do this automatically, calling Whitson through an API or connecting to a database they have. So that is a more automated way, and instead of using the interface.
Yeah, exactly. And a lot of Snowflake connection, Databricks, and any type of direct connection basically to your internal database. You have like a WellView database that you want to connect, all the Wellbore data, the well deviation service, everything that Milan showed today that was sort of painfully done manually on purpose, just so you guys could learn like the manual process of doing it. It's basically done automatically for 99% of the companies that we work with. Through either the API connection, Snowflake, Databricks, or similar connections.
Yep, and then we reach the end of the course. Let's go back to the table of contents. Maybe there we can see what we have covered, take an overview. We didn't get too much interaction, but I think there were a lot of comments in the in the chat, so I think that was very good. Yeah, that's what we covered, and the exercises we covered. Okay, these exercises here. So I think we reached the end, unless you have any additional questions.
I think there was a question from Michael just on like your thoughts on using, if you had rod pump and plunger lift, like what's the issues with calculating the bottomhole pressure just through the tubing, making some assumptions on the average rates that are actually flowing through the tubing instead of doing it through the casing side or through the quiet side. I think that was the only question I thought you'd maybe want to just elaborate on a little bit, and otherwise it was mainly questions related to the software usage.
Yep, I think we covered this. Maybe you were not in the call, but I mentioned that in plunger lift the rate will change quite dynamically in matters of minutes or like hours, and the bottom hole pressure in consequence would also change quite dynamically within that range. But I if you want to use that for any reservoir engineering workflow, it's really a bit it's too detailed, it's too granular for and so what is done currently is that you take an average of this, you take how much was produced during the day, but you also should take into account how many cycles so you are producing, such that you get the rate which is representative. Even though the rate will be changing, you simply say, well, I have an average rate that has been produced throughout the day, and then you get like an average bottom hole pressure. Another option is that you have the liquid level, and if you have no packer here, which is usually the case, you want to use the annulus as a lung to allow you to to push the piston, to push the plunger higher or to push it. So then you can take the level measurement, and then you can do a calculation down to the formation. So that's another option you have for plunger lift. And again, this liquid level measured you don't have is not so, it doesn't have such a high resolution. It's made like every, you have an average for the day, and that's the value that it will be used, the average. Although it will change during the plunger cycle.
Perfect.
Was a question here, the tuning factors is really difficult to say. What you can do is you can do it later in the software. You have a kind of in the nodal, you have gradient calculation, and you can try to find out how much is, so what percentage you're having has a friction and gravity. And from there, see still that if you're keeping the physics, because it might be that you're tuning, increasing too much artificially the friction component, and even though you're getting a good match, at the end is simply unphysical because it becomes too large. But we don't put. I think there are no bounds. It's like you just have to. Yeah, that's why I say use it carefully, because you might get some values which might be non-physical. That's why it helps if you have some more points later in time, you can compare, or if you have a neighboring well, you apply the same factors and see how how is the comparison, and then that helps you to have trust or not on the coefficient. Yeah, I see there is a jet pump. So features coming in the software, chokes, wellhead downhole chokes. They're coming hopefully in May soon, in about 2 weeks, I think. So they're in the pipeline. You will be able to put a choke, and jet pumps. We hopefully have them before the summer. Yeah. So far, I think there is no workaround for jet pumps. It needs a special. It needs to be implemented in the software. There is no workaround.
Yep.
Yeah,
Perfect.
foam lift. There is a bit of a debate. So foaming affects affects the holdup that you're having on your is like what you're referring to is like soap sticks, is it? Or
I can come off mute if we're getting to a question and answer session, if that's all right.
that's fine. I think I don't have any
Yep.
more to cover. So yeah, that's
Yeah, no, I was just curious because to your point, or basically either for continuous injection down a backside or cap string or even just soap, soap sticks, like how you basically adjust for the fact that you're having a foamed fluid column and how far that column's making it and all of that. If anybody, if there's any significant work done on that, it's just kind of a blank area for me.
Yeah, I don't think so. The way people capture the effect it has in your calculation, in your correlation, is it's changed the holdup. So the holdup that you're getting, it will be something different and will be, let's say, more gassy. It will be less liquid because you trap the liquid in this foam. And people modeling that, so either modify the correlation in some way, and usually it's changing the surface tension. That with the amount of foam, they have some surface tension change between the oil, the liquid, and the gas, and that surface tension change gives you a different holdup. But that's not implemented here in the software. So I'm not sure if there. At this time I don't can think of a workaround to do it, but that will be the effect it will have.
Thank you.
All right. I think we can call it a course. And thank you so much, everyone. Thanks, Milan, for the great course. And we'll wrap it up here.
Yep. Thank you very much, everyone. Good luck. Happy Whitson Plus.
Thanks, Milan. Appreciate it.